Good day and welcome to the fourth part of our discussion on integration by parts. So let me give you the quick reminder. Integration by parts is described by the formula that the integral of u dv is uv minus the integral of v du. And we've talked a bit in the previous videos about good choices for u, the fact that we can use integration by parts multiple times, also the fact that we can combine together our techniques of integrations. Maybe we'll need an integration by parts and a substitution in the same problem, and they could come in either order. And also the fact that we can evaluate definite integrals with a substitution. So let's go ahead and investigate a few more examples. We will begin with the antiderivative of natural log over x squared. And let me just go ahead and note for convenience, this is really the integral of the natural log of x times 1 over x squared. And it's tempting to try maybe a previous technique of integration, but in its current form, I'm going to note a substitution wouldn't quite work. But just for fun, to the side here, if you had the antiderivative of natural log over x, this is something you could evaluate very quickly and efficiently with a substitution. For u equals the natural log of x, du is 1 over x. So our integrand is made up of a u du. So we would have the integral of u du, which is 1/2 u squared, and we resubstitute back in. But that's not quite what we have in the current example because it's an x squared instead of a single x. So what that's going to force us to do is attempt integration by parts. And when we use integration by parts, we have this choice to make. What's going to play the role of u? What's going to play the role of dv? The natural log of x is much simpler to differentiate than it is to integrate. That prompts us to use u equals the natural log and dv 1 over x squared. There's no guarantee that it will work, but that's certainly going to be my first choice. du is 1 over x, and v would be the antiderivative of 1 over x squared. So let's see what we end up with. uv minus the integral of v du. With the v, you have a negative sign. So that negative sign can be pulled in front of the integral, turning the minus into a plus. And then what we are integrating is 1 over x times 1 over x. And we don't have to think too hard about this resulting indefinite integral because we just evaluated it. What we are left with is minus 1 over x natural log x minus 1 over x. And we remember our plus c because it's an indefinite integral. Moving on, in our second example, we need to antidifferentiate t cubed e to the minus t squared. Now, our intuition, I hope, when we look at this, is a polynomial times an exponential. So integration by parts seems like a very reasonable option. But upon closer inspection, you might notice we have this t squared inside our exponential. So instead of applying integration by parts to start with, let's begin with a substitution. And the substitution that we might want to think about attempting is, let's go ahead and I'll call it w. Make w t squared. So if w is t squared, dw would be 2t dt. So we might have to rewrite our integrand a bit. So note t cubed, you can write that as t squared times t. And then we have e to the minus t squared. So in terms of w's, the t dt is 1/2 dw. The t squared inside our exponential is a w, and the t squared in front of the exponential is a w. And with that in mind, I think you are in a perfect position to finish up this problem. So go ahead, pause your video, make the substitution, evaluate the integral. So now that you've thought about this, if we express it in terms of w's, we have that 1/2 pulling out front, and we're left with w e to the minus w dw. And this is an ideal scenario for integration by parts. A power of our variable times an exponential. And note, there could really be any constant in this exponential, and we could handle it with integration by parts. In this case, it just happens to be a -1 with the w. So using integration by parts, we need a choice for u and dv. Using our previous experience, we'll choose u to be w and dv to be e to the minus w dw. So v is minus e to the minus w, and du is dw. So applying our integration by parts, we have this 1/2 hanging around front. Then uv would be minus w e to the minus w. And we're subtracting away the integral of v du. So that would be a minus e to the minus w dw. And once again, if we pull that minus sign out front, it turns the minus which is there into a plus. And while we're doing this next step, I'm just going to go ahead and distribute the 1/2 through. So we have a minus 1/2 w e to the minus w. Then we have the 1/2, and it's hitting this antiderivative. But the antiderivative of e to the minus w is minus e to the minus w. So minus e to the minus w plus c. And let me go ahead and just make a small note to the side here to make sure we are all on the same page. If you would like to integrate e to the kx, where k is any non-zero constant, this is an example we have specifically encountered in the past. The value would be 1 over k e to the kx plus c, and if you're unsure why that is the case, you could evaluate this using a substitution. In our case, the k value is -1, so we have 1 over -1, which is the minus. Note we're not quite done with the integral, so hopefully I haven't distracted us from our goal. We need to resubstitute. Each and every w that we see needs to become a t squared. So minus 1/2 t squared e to the minus t squared minus 1/2 e to the minus t squared plus c. So once again, it's perfectly reasonable to combine together multiple techniques of integration. In this case, it was a substitution followed by an integration by parts. And the more we practice, the more efficient we will become in recognizing the necessary techniques. But with integration, don't ever be afraid to try something and see if it works out. Worst case scenario, we have learned something that does not work, and we just start off again on a fresh piece of paper. So let's go ahead and finish with one more additional, slightly involved example. For our remaining example, we are going to anti-differentiate cosine of the square root of x. And I don't think it's obvious at first glance how we should evaluate this integral. But instead, we're going to have to talk our way through it, and hopefully from seeing the example now, when similar things appear later on, we'll be prepared. So for the antiderivative of cosine of square root of x, going through my mental process, I don't know the antiderivative off the top of my head. I can't easily manipulate this algebraically, if at all. I don't see an obvious substitution, but it also doesn't really look like something that's conducive or well suited for integration by parts. And that kind of exhausts our list. So what about this is making it difficult? Sometimes if I'm unsure of the technique to use, I can really think about maybe eliminating the difficulty. So what's troublesome to me is this square root of x. If that was just an x by itself, we could evaluate with no problem. So let's go ahead and try a substitution. Maybe we could let w be the square root of x. And that was really a statement, not a question. Let's see what happens. If we let w be the square root of x, then dw must be 1 over 2 square roots of x dx. Well, let's see how we can handle this. We need to go from all x's to all w's. So we need to rewrite dx in terms of dw. So note dx can be 2 square root of x dw, but the square root of x is w. So dx can be written as 2w dw. So 2 is a constant we can pull out front, and what we are left with is cosine w times w dw. And I feel as though there's almost a tendency to look at this and think, wow, we made it more difficult. But remember, in mathematics, sometimes you have to complicate in order to simplify. And in this case, this integral that at first glance might look a bit more involved is actually something we can evaluate quite efficiently. We can evaluate this using integration by parts. So at this point, I would like you to pause the video, give yourself maybe 2 minutes to finish up this problem, and do not forget to resubstitute. And now using integration by parts, we'll choose u to be w and dv to be cosine of w. So v would have to be the antiderivative of cosine, which is sine, and du would simply be dw. So our integration by parts is going to tell us uv, so 2w sine w. And I'm just going to go ahead and distribute this 2 through as we go along. Minus the integral, and note we have the 2 that distribute it, of v du. So sine w dw. And the antiderivative of sine is minus cosine. So we have the minus sign which is hanging around, and we're going to get another minus involved with the antiderivative of sine, plus c. In our final step, we resubstitute. Each and every w we see needs to be replaced with a square root of x. Which completes this example. Now, as usual, we are in a perfect position to practice more examples. And if you look at the remaining 3 examples on this 6th page of the note handout, these are the examples if we were meeting face-to-face that I would be writing on the board and having you all spend anywhere from, say, 10 to 15 minutes working on. So before viewing the next video, give a nice, honest effort in terms of evaluating these 3 integrals. And I'll give you a hint. They are all going to involve in some way, shape, or form integration by parts, but in that middle example, it might help to first make a substitution. So stay tuned and take care.